Good afternoon, everyone. Welcome to the last of the press briefings for the combined Division of Planetary Sciences and European Planetary Science Congress conference on today, Thursday, October 20th, 2016. My name is Constantine Tsang. I'm the Deputy Press Officer for DPS, and along with my colleagues, Shantanu Naidu, DPS Press Officer, Anita Hayward, EPSC Press Officer, and Rick Feinberg, AAS Press Officer, would like to welcome you today at this press conference. Before we begin, I would ask you to mute or turn off your phones, and also if you could keep your applause after each talk, that would be great. Today we have 4 speakers talking about a range of incredibly interesting topics from throughout the whole solar system. We begin with Vishnu Reddy, University of Arizona, talking about the asteroid Psyche, followed by Katherine de Kleer, University of California at Berkeley, then Linda Spilker, NASA Jet Propulsion Laboratory, and finally Athena Coustenis, Paris Observatory, who will join us at the end of the meeting. And without further ado, Vishnu.
All right, good afternoon. So today I'm going to talk about a very interesting result from asteroid Psyche. So to get you started, what are asteroids? Asteroids are mostly rocky bodies that go around the sun between the orbits of Mars and Jupiter. There are about 800,000 of them, and I show all 800,000 of them in this plot. Psyche itself is that yellow line that's going around the sun. It's actually not the largest asteroid. The largest asteroid itself is asteroid Vesta. The largest body in the asteroid belt is not an asteroid, it's dwarf planet Ceres. Psyche is in between dwarf planet Ceres and asteroid Vesta. It's about 226 kilometers across. Its taxonomic type is M. We're going to talk a little bit more what that means. And one of the interesting things about Psyche is that when we first looked at it with radar, it had a very high radar albedo. And that suggested that Psyche might be mostly metallic. Even with some porosity, it had a very high density, almost 4.5 grams per cubic centimeter. So this made Psyche a very interesting target for us to go and study it with a range of ground-based assets. So we started an observational campaign last year. So here are all the telescopes we used. To my far right are the Keck telescopes on Mauna Kea, Hawaii. Then we had the NASA IRTF, the Arecibo Planetary Radar, and also the Magellan telescope in Chile. So what we did with Keck and Magellan were adaptive optic imaging. Al Conrad and IMCA led these efforts. I'm not going to talk about those results. Also at the same time, Arecibo radar did the shape model and also got a rotationally resolved radar albedo to find out if the distribution of metal on Psyche is uniform or not. We're going to briefly touch on that, but primarily there's a talk tomorrow by Mike Shepard and his colleagues who are going to focus on that. What we're going to look at are IRTF observations. These are primarily in the near infrared and mid infrared. That's the wavelength range that we usually don't see with the human eye, further from the reddest wavelength range that we can see. So we'll focus primarily on the IRTF observations today. And these 2 observations that I talk about today are actually published in a paper by Dries Kleer, and a paper is already in review by Juan Sanchez. So let's get to the results directly. So on the top, you see a NASA IRTF spectrum. What you see in the black line is the spectrum. At those wavelength range, you have a thermal emission that we have to correct for before you can actually look at the absorption band. The absorption band itself is a small dip below the red line at about 3 microns. This is very similar to what we see on some carbonaceous chondrite meteorites in the laboratory. So the spectrum from the lab is shown below. And these meteorites are usually rich in volatiles. So for example, water or OH in the minerals that are predominant in these meteorites also show this absorption band. And we actually observe Psyche as it rotates around its axis, and we were able to map the distribution of this 3 micron band. So when we combine all these observations, we get a very interesting plot. What you see in this plot is longitude on the bottom axis, body center longitude, a radar albedo on the far right side, y-axis, and absorption band depth on towards the left axis. And the blue dots show the absorption band due to a mineral called pyroxene. And pyroxene is thought to be on the surface of Psyche in the form of a regolith that is mixed with metal. So an interesting thing we see here is that as the radar albedo drops, which are those black data points, the pyroxene absorption depth increases, which suggests that as the regolith on surface of Psyche increases, the amount of metal goes down, which makes sense because you have a thick regolith layer. You're obviously not able to detect any metal that is there, or that mineral is dominating the surface. The red lines you see on this plot show where we've detected the 3-micron band. And there's an interesting location where which we detected this 3-micron band that we were able to correlate with the radar shape model. So in the next plot, I show the radar shape model to the far right, which is actually rotating. And the bottom, we have a map from Juan Sanchez's paper. The interesting thing is that a 3-micron band is detected where there's an 85-kilometer crater close in the southern hemisphere. So we believe that based on the radar data and the location of this absorption band centered on this crater, that there might have been a dark impactor that hit Psyche in its past, and that's possibly causing it. So this is not something new. We actually see this on Vesta. Asteroid Vesta was observed by the Dawn spacecraft a few years ago, where we've detected a number of dark craters on its surface. I'll show you an example. And the work we have done shows that carbonaceous chondrites, which are a particularly dark type of meteorites rich in volatiles, impacted the surface of Vesta and actually delivered volatiles and organic material to its surface. There's also another way where you can create water or OH on the surface. This is using solar wind. So solar wind bombarding the silicates on the surface of Psyche would cause minerals to break down and form bonds with the oxygen in the regolith, creating OH or H2O later when the surface is saturated. So this is also an option. And to summarize, so we've done multi-wavelength observations of Psyche, and from these observations, what we found is that the surface has possibly water or OH on its surface in the regolith. And interesting thing is that we have an 85-kilometer crater that is also showing evidence for this. And we think there are two possible mechanisms, like I talked about, delivery by impactors or solar wind. And with that, I will ask Katherine to come and talk about IO.
All right, great. So I will be talking about results from an ongoing high-cadence observing campaign focused on Io's volcanism. So Io is the innermost satellite of Jupiter, and it's the most volcanically active object in the solar system. It's also the only place other than Earth where we see large-scale volcanic eruptions occurring in progress, so we can look at them in real time. Sorry, lost my train of thought. We can look at these occurring in real time, and it is the only place then that we can look to understand how geological processes like volcanism are different on planets and moons that are diverse. So Io and Earth are very different. They have very different compositions, gravities, histories. The volcanism has a different heat source. So how do these factors affect how geological activity occurs differently on different planets and moons? So Io hosts a wide range of different styles of volcanic activity, including lava lakes, lava flows, large-scale outburst eruptions, some of which produce plumes that go 100 kilometers or more off the surface of Io, surface deposits. The majority of these images come from the Galileo spacecraft. all of these types of volcanic activity that we see on Io can be an order of magnitude or more larger in scale than anything we see on Earth today. And in fact, the style and scale of the activity that we see on Io may be more representative of the activity we saw on, or we know occurred on Earth and all the other terrestrial planets earlier in the history of the solar system. So people have argued that Io may be our sort of single window into the past, into understanding these processes that occurred on early Earth. Io's volcanic activity is very time variable. It looks different every time we look at it, day to day, hour to hour. These volcanic events can evolve. And so to characterize this volcanic activity, we really need to look at it with high frequency over a long time baseline. So myself and Imke de Pater at UC Berkeley have been conducting a high cadence observing campaign going back to 2013. The campaign is ongoing, but through the end of 2015, we made observations on 100 different nights at the Keck and Gemini North telescopes on Mauna Kea in Hawaii. During this time, we tracked the evolution of about 50 different individual active volcanic regions, and we do this using adaptive optics. So this is what Io looks like if you're not using adaptive optics. It's basically an unresolved blob, and then as soon as you turn on the adaptive optics, you can resolve out the disk and these individual hotspots. So these bright spots that you see are thermal emission from individual active volcanic regions. So this is what a sampling of the data set looks like. These images represent data taken on all 100 nights, both telescopes and a variety of wavelengths. So they're roughly arranged from top to bottom in order of increasing wavelengths. So towards the bottom, at the longer wavelengths, you see that the hotspots stand out more prominently against the disk. So because we can resolve these individual volcanic features, we can identify which volcanoes are responsible for them, and we can look at their evolution over time. So here's what we saw. This is an animation which is showing all of the detections that we made during this time period. It's stepping through time, and this is a full map of Io that you're seeing. So each of these red circles that appears is a new detection that we made. So many of these detections, as you can see, are of the same lava flow or the same eruption. The size of the circle corresponds to the brightness of the detection. And you can see that there are some spots that seem to stay active for the entire time at a relatively constant brightness. There are others that seem to stay active but move around a little bit. And there are a number of these ones that just flash on and then disappear, particularly the bright ones. So let's focus on those for a minute. This map is just a collapse of the movie across the time axis. So you're seeing all of these different detections overplotted, and I've color-coded them. So in blue, you're seeing these ones that were consistently active over the entire period of observation, or a year or more specifically. And in red, you see these ones that flashed on and then disappeared, which I've labeled as the sudden brightening events. And so you immediately see that these separate out spatially into the two hemispheres. So this is inconsistent with any of the models we have for how the heating should be occurring in Io's interior, and is really intriguing. In addition, you see that these sudden brightening ones, and in particular the largest ones, are occurring at relatively high latitudes. So I can't tell you the answer to why this is happening, but we can get some clues by looking at the cluster of hotspots that you see in the southern hemisphere, the red ones there. So you see that they're all closely spaced in location. In addition, their timing is really intriguing. So I'll go back to the movie and highlight them here. So you see at the beginning of the movie, there were those two bright ones just all the way to the left, and the movie will cycle around so you can see it again. And after that, you see that the bright eruptions move progressively in an eastward direction over the course of observation. And these are separated by about 500 kilometers on Io's surface, each of them. So this is very suggestive of some mechanism that is triggering either the volcanoes moving progressively in one direction, or even a mutual triggering mechanism where you have one of these volcanoes triggering the other one to erupt. This is certainly not conclusive evidence, but the timing and the spatial correlation are intriguing. And in addition, if you have a mechanism like this, it can explain why you see these volcanoes so well clustered. So it may be that the spatial distribution is not even representative of the heating in the interior, but is just due to some more superficial mechanism. So this is something we still don't have an answer to, but yeah, lots of intriguing ideas. So I want to now focus in on one particular volcano, and that's Loki Patera. So Loki Patera is the most powerful of these persistently active hotspots, and it's been active for decades. So it's a warm, dark feature that's about 200 kilometers across, and home of the Loki Patera Planetary Park, if you want to go visit. So between the late 1980s and about 2002, it was seen to brighten periodically by about an order of magnitude. And these brightenings happen about once every 1 to 2 years. Between 2002 and 2009, as you can see, there was no activity detected there. Then in 2009, we started detecting these brightening events again, and we saw 5 of them between 2009 and now, and 2016. So one thing that's really interesting about the new detections is that prior to 2002, data from Galileo and some ground-based observations indicated that when these brightening events are occurring, the brightest spot within the Patera is moving in a counterclockwise direction around the Patera during the bright phase. Our observations after 2009 suggest exactly the opposite. So here, these are data points from our observations, and you can see the uncertainties in the location of emission, and they're colored according to the phase of the brightening cycle. So the red points are observations that were made at the beginning of the brightening cycle, and the purple are made towards the end. So you can really see that there's this counterclockwise motion, which is exactly the opposite of what was seen before. We don't exactly know what mechanism could be causing this reversal. We have some ideas. But in fact, even the mechanism causing the brightenings at Loki Patera to begin with is still in debate. So again, this is a puzzle that we're very interested in and are actively pursuing. So with that, I will conclude and just put up my summary for a moment, and then I guess I should exit this and hit the reset button.
Good afternoon. I'm going to share with you some of the exciting potential for the final year of Cassini. We're in that final year right now. In fact, very shortly we're going to start a dive very close to the rings and the planet, and you can think of that dive kind of like the final chapter of one of the most incredible books you've ever read. You're looking forward to that final chapter and you don't know what you'll find inside it. And for me, the headline of Cassini's final year won't be just the plunge into Saturn at the end of the mission, but instead will be the incredible science that we collect. And staying with the book analogy, it's kind of like the final plunge is like the period on the end of that sentence on the last paragraph of the chapter. There's so much more to it, and I'm going to show you how much bigger the grand finale is than just the final plunge. So to set up for the grand finale, this graphic shows you the Cassini mission. We've been in orbit around Saturn 13 years by the end of the mission. A couple of the key highlights. By the end of the mission, we'll have flown by the giant moon Titan 127 times. Now, Titan is about the size of the planet Mercury. It has liquid methane lakes and seas at the North Pole and a global ocean of liquid water underneath its icy crust. Tiny Enceladus, only 1/10 the size of Titan, also has a global ocean underneath its icy crust and active geysers going off at the South Pole. And of course, our final orbits at the end of the mission, proximal orbits that are part of our grand finale. Well, what are some of the key characteristics of these 42 orbits toward the end of the mission? The orbits shown in gray are the F-ring orbits, about 7 days long. We pull the periaps very close to the outermost edge of Saturn's rings. The F-ring just hugs the edge of those rings. We'll get incredible views of the F ring, the A and B rings at Saturn, and that family of tiny ring moons that hovers just outside the main rings and in part creates the detailed structure that you see there. Then we have 22 orbits with a single Titan flyby. We hop across the rings, actually dive in between them, and spend 22 orbits in a very interesting configuration, truly like a brand new mission. You see those orbits in blue, and then of course our final impact orbit is shown in orange. Now, if you could ride along with the Cassini spacecraft, hanging tightly to that high-gain antenna, what might you see? If you could do that, here's a movie. You're coming in at 74,000 miles per hour, coming in along the day side, swooping through that gap, and going outward. You can see the sun and the Milky Way background. We repeat this, and each time we have different science objectives: the planet itself, sometimes the rings, sometimes the environment in between the rings and the planet. We're flying through a gap that's only about 2,000 kilometers wide. What are some of the objectives of the grand finale? Well, first and foremost, it's bringing us closer to Saturn than we've ever been before. This is truly a brand new mission. It's very similar in the science we can do to the Juno mission at Jupiter, and we're doing the two missions at the same time to be able to compare both Saturn and Jupiter. Also, we're flying in a place that no spacecraft has ever flown before. And when you do that, when you fly closer or someplace new, you're bound to make discoveries. And so we're really curious to see what those might be. Well, we're going into this region really for the unique science as well as planetary protection. For planetary protection, since Cassini is running low on fuel, we have to figure out a way to dispose of the spacecraft and guarantee it will not impact those two ocean worlds I talked about, Enceladus and Titan. And so we satisfy planetary protection and at the same time gather a tremendous amount of unique science. The first involves the planet itself. We're going to get a detailed idea of what Saturn looks like on the inside. Imagine if you could peel back the clouds of Saturn and see how differentiated is it? Does it have a tiny rocky core? If so, how big is that core? What does it look like as you go further out? Is it a little bit lumpy inside? How is it coupled to the winds that you see that circulate in the atmosphere that's visible to our cameras? And then that convective region that has currents flowing in it that create the magnetic field. What's the size of that region? How is it structured inside the planet? And these close flybys will allow us to measure both the gravity and magnetic fields with exquisite precision. Another thing I'm very excited about as a ring scientist is to measure the mass of Saturn's main rings for the first time. Right now, that mass is uncertain by about 100%. If the rings are more massive, perhaps they formed at the same time as Saturn. If they're less massive, then perhaps a centaur or a comet or a moon wandered in too close to Saturn, was torn apart by Saturn's gravity, and created the rings. So we can answer the question, how old are the rings? And of course, flying through that region will make direct measurements of the environment that's there, from Saturn's ionosphere to the inner radiation belts, to the auroral regions at the north and south poles, and actually measure the composition of the rings, that the tiniest ring particles get charged, spiral along the field lines, and go into our detector that can break apart the particle and tell us what it's made of. Is it carbon, silicates, what else besides the 99% water ice? And then for the atmosphere of Saturn, we're going to be basically in the last 5 orbits dipping our toe into the atmosphere and making direct measurements of the helium abundance and the other constituents besides hydrogen that make up the planet. And of course, we're going to get very high resolution views of the rings and the planet. For the rings, this will be the highest resolution we've seen since 2004, right after Saturn orbit insertion. For the planet itself, we'll study the hurricanes that Cassini discovered, as well as the giant hexagon that circles at the North Pole. And here's the timeline for that grand finale. We go into the F-ring orbits on November 30th, and what you're seeing here is each of those 20 orbits. You're fixed in the Saturn frame, so you're seeing the longitudinal coverage coming from Saturn. After that, on April 22nd, we have our final flyby of Titan. Very shortly, you'll see Titan. There, Titan comes and curves the orbit to go from outside the F-ring to just in that gap between the innermost ring and the planet. Now, a flyby of Titan gives us the equivalent of about 1/3 of the total amount of fuel that's on board Cassini. Titan is a huge moon and allows us to really bend that trajectory. And then we have a series of 22 orbits through after that. On April 23rd, that's the start of our grand finale set of orbits. Again, Saturn is not rotating, so you're seeing the longitudinal coverage there. we have 9 non-targeted flybys of Titan. These are 100,000 to 200,000 kilometers away. And even though we're that far away from Titan, it's big enough that it nudges us ever closer to the planet. So we start our orbits very close to the outer edge of the D-ring and then walk our way in toward the planet. Then on September 22nd, we have September 11th, sorry, we have our last non-targeted flyby of Titan, and its gravity is sufficient to guarantee that on that final orbit will impact the planet. And on September 15th, about 5 a.m. Pacific time, that's when we'll impact Saturn. And the reason we're doing this, as I said, is to protect the 2 worlds that we know have liquid water oceans, Titan and Enceladus. And so for me, the Cassini grand finale is really about a lot more than that final plunge. If you think about it, the Cassini mission has really revolutionized our views of the Saturn system, from the planet to the rings to the icy moons. Not only have we revolutionized our view of the Saturn system, but of our solar system as a whole, and also of the planets that circle other stars. Could some of those other planets around other stars have tiny moons with liquid water oceans? And could you perhaps find life in those oceans? So the Cassini mission has truly paved the way for future missions to go back, look at these worlds in our own solar system, and answer the question, is there life beyond Earth? Thank you.
Hi, my name is Athena Coustenis, and I work at Paris Meudon Observatory. It's a pleasure to be here today and follow up on what Linda was actually just saying, because I am going to also be discussing very much results from the Cassini mission. I'm going to be focusing on Titan. Titan has been one of the most exciting and unique objects in the solar system that we've had a chance to closely look at with Cassini. Previous to what, it has been explored by a few missions. One of them was the Voyager mission, which you can see over there, flew by Titan and in the Saturnian system in 1980. 10 years later, more than 10 years later, I was doing my PhD and I was working on Titan data from the Voyager mission. The Voyager mission was 1 flyby. Now you can imagine, with all those flybys, we've got 42 more orbits left, out of which we'll have several flybys of Titan with the Cassini mission. It's such a huge amount of data that I think at least 3 generations of astronomers coming on will be able to analyze and work on that wealth of data in the coming years. But the thing with Titan is not only it's exciting because of the several features you've seen on its surface. I'm sure you've all noticed that there are very many similarities on Titan's surface with our own planet, but because essentially of this atmosphere that covers it entirely, the atmosphere being composed essentially of nitrogen, as on our own planet, with methane as the secondary trace gas in there. And whoever says nitrogen and methane immediately knows that we're going to get organic chemistry. We're going to get hydrocarbons, we're going to get nitriles. So Titan's atmosphere is a very exciting place to go to, and even more so because Titan has seasons, because you can see this obliquity here as it follows Saturn around the sun during 30 years. You can see the 30 years here. Titan has seasons, and the seasons are 7.5 years, so you can imagine you have 7.5 years of winter to go skiing, 7.5 years of summer to go to the beach. It's a wonderful place to be, and I can't help mentioning also that you have instead of 24 hours, you've got 8 hours for the daytime and 8 hours for the nighttime. So beautiful place to go. Only trouble is the temperature. You lose a lot when you go on Titan, pretty much like today when you go from outside down here. During the Cassini mission, those 13 years, yeah, I can see coats and scarves. We'll be able to have covered out of those 30 years just 2 of those seasons, and you can see it here highlighted from the time we arrived at Cassini with 2004 to today. Cassini extended mission will have just 2 of these seasons covered. And actually during our mission, Cassini mission, we went by again the epoch of the Voyager 1 flyby to see if we were finding the same things as from the Voyager analysis and if the atmosphere behaved in the same way. And indeed, it did pretty much. So we weren't very much prepared for all the excitement that I'm going to show you in the coming slides, because Titan's chemistry, as I said, is very complex. You can see here this schematic that goes from the upper part of the atmosphere with the nitrogen and methane all the way through the atmosphere with all this ionization, dissociation, photolysis processes to create more and more complex molecules that all go to and be deposited on Titan's surface at some point, and the famous tholins that are these big aggregates of organics. And you can see this is a very busy diagram, but what it's trying to tell you is that you have an organic and a chronological cycle on Titan, pretty much like what water does on the Earth, but this is methane here, where you have a cycle of methane, you have evaporation, you can have rain, you can have methane ice also on the surface and condensate form in the atmosphere. And this leads to the formation of all these exciting surface features that you see today on Titan, including the lakes, including possible cryovolcanoes, including mountains and dunes, all these things we didn't expect to see. In a part of the atmosphere that is called the stratosphere, that is about here, we find all this organic chemistry coming together, and we look at it with the Sears instrument, the composite infrared spectrometer on board of Cassini. And this is what we call a spectrum, and a spectrum is a manifestation of all the composition, the chemical composition we have in Titan's stratosphere. Usual suspects, like I said, you have the nitriles, you have a lot of hydrocarbons here, and you have some opportunity to see some oxygen compounds that are not coming from inside Titan. So what we saw is there was a strong differences in these gases composition that increased dramatically after we went through the equinox, essentially after 2010 or 2012. And just look at these regions here. The little lines that you see here are, of course, the signatures of all these trace gases in Titan's atmosphere. You can see in this region here in October 2010, we had just this component here, CO2. By the time we went to May 2013, all these other molecules like HC3N and benzene pop up. And you can see just by that there is going to be a significant difference in the composition. And indeed, following a 40-degree decrease in temperature within 4 years in the stratosphere of Titan around the South Polar region, the South Pole lost 40 degrees in temperature within 4 years. Dramatic decrease in temperature associated also with a very strong enhancement in some of these trace gases. Now, if you look at the blue lines, it's 50 degrees north, the green lines is 50 degrees south, so we're at higher latitudes, but not close to the poles. Black lines is just the North Pole here. You can see nothing much is happening. It remains very much enhanced in composition because it just came out of winter. It's going into summer. The South Pole now is going into winter. These are all the red lines that you can see here. I'm talking orders of magnitude increase in many of these constituents. The South Polar region is becoming a huge reservoir of enhanced material in terms of gases, but not only, also condensate, also little icy particles in the atmosphere of Titan. And all of these things are part of this scheme here where you start with nitrogen and methane and you produce all these molecules into the atmosphere. Some of them we've seen. These are the dark blue species that you see here. Some of them we have not observed yet, although they are predicted in the photochemical models and in the chemical paths as you see here. So what do we do now? Well, it's amazing that this strong difference with the South Pole going into winter has come on so quickly. We expected to see this enhancement in gases. What we didn't expect is for this to come on within months after we went past the equinox. The South Pole started being increased in all of these gaseous constituents within months. And after a year, we see this tremendous increase that I just showed you. So what do we want to do? Well, we want to go and look to for more complex organics. We want to understand how complicated is this organic chemistry in Titan's atmosphere. It's very important to see what is the degree of complexity here. So we're going to look for more complex organics because this is our opportunity in the South Polar region with all this increase of the molecular content to look for strange, weird, weak, complicated molecules like propionitrile and butane, much more even than benzene. So all of these molecules that we have not been able to observe before, not even in the North Polar region, we're hunting for in the South. And of course, why do we do this? Because organic chemistry, as Linda mentioned before, is also very important for us when we explore the solar system. It's one of the essential requirements for life and for habitability that we look for in the solar system. Liquid water, of course, the essential elements, the SNOPs is the organic chemistry. We need to have chemical energy and in a stable environment for the metabolism to occur. So on these bodies where the habitability has now moved from the surface underneath into liquid water, oceans that possibly exist under the surface, Europa, you've heard of, Ganymede, we're going to be looking with JUICE, the mission that is planned from the European Space Agency, and with the Europa Clipper mission from the US. And for Saturn, we have Titan and Enceladus. Enceladus, of course, the wonderful moon that ejects all those geysers of water vapor out in the atmosphere. So we're looking for these conditions of habitability in the outer solar system. Titan is a very good candidate. We think it has an undersurface ocean, and it's the only one that has this very, very important organic chemistry. So I'll stop here. Thank you.
All right, we move to the quick Q&A part of this briefing. We'll take some questions from the floor, and then we'll go to the online audience, and then we'll move back to the floor to finish. Shantanu has the microphone, and if you could state your name, affiliation, and then your question.
It's for Linda. For the very final moments of Cassini, what kinds of data are going to be taken during the final plunge, and what do you expect to get returned to Earth?
The key data will be, excuse me, the key data we'll be collecting for the final plunge are data of the composition of the atmosphere. The ion and neutral mass spectrometer will be pointed in the direction to scoop up that atmosphere, and we'll be sending the data back as quickly as possible. So in those final seconds, we'll get as deep as we can into Saturn's atmosphere. This might potentially help with a future planetary probe mission or something that would perhaps use Saturn's atmosphere for aerobraking.
Do we have questions from the back, Rick?
Yes, we have several from the web. The first one is from Kelly Beatty of Sky and Telescope for Katherine. He says, it's amazing that you can pinpoint the locations of the volcanoes so precisely. What is the angular resolution of the adaptive optics imaging, and what does that correspond to spatially at Io's distance in terms of linear distance?
Right, so each pixel, the angular size of each pixel is 100th of an arc second, which corresponds to about 30 kilometers on Io's surface. The actual resolution is a few pixels, and so depending on the exact wavelength that you're looking at, the angular resolution can be anywhere from a little over 100 kilometers on Io's surface to a few hundred kilometers.
Okay, Kelly also has a question for Athena. He asks, how might the dramatic change in upper atmospheric chemistry hint about what's going on lower down in the troposphere? And particularly, what compounds might be precipitating onto the surface? In other words, does the composition of Titan's rain change with the seasons?
Yeah, so all of this is obviously connected, and what I was showing today was the part of the atmosphere that we call the stratosphere, and that was observed with the CIRS instrument. The upper parts of the atmosphere are observed with the INMS and other instruments, the UVS and so on. Lower in the atmosphere, we've been fortunate enough to have the Huygens probe that went through Titan's atmosphere all the way down to the ground. So we're able to combine measurements from the various instruments and sort of follow through the chemistry and its evolution through the atmosphere. And this evolution is quite dramatic, as I was showing in that schematic. The molecules grow as you go further down into the atmosphere. They become more complex, and some of the molecules coagulate and combine. By the time they get to the surface, these are really very complicated aggregates and compounds, organics that can possibly cover huge areas on the surface, and this is something that we actually observe in some regions on Titan. Would the seasons affect that? Yes, very much. Even the solar illumination currently, when it changes briefly, you don't have to go throughout a whole season, it will change the photolysis in the upper atmosphere, and so hence the whole process of what gets to the surface. And this is why I think some of the differences and the variations we observe on the surface features are due to the atmospheric changes.
I can maybe just add quickly, it probably wouldn't change the composition of the rain, which we think is essentially methane with some ethane. That's more driven by the temperature, but maybe you can get some of these other particles entrained in that, but not the absolute composition of the rain.
Yeah, and hydrocarbons, essentially, the rain is made of rain or snow, actually, because we don't know. Some of the molecules, some of the compounds become ice in the lower layers of the atmosphere, so we could even have snow falling down. Composition will not change very much. It will change with respect to the higher atmosphere.
Molly Lochtwalla from the Planetary Society again for Katherine. There is, of course, a spacecraft in orbit at Jupiter right now. I'm wondering if you guys are communicating at all with the Juno team about what you're finding about activity at Io and how that might affect the kinds of things that Juno is observing.
Right. We certainly are communicating with the Juno team. So Juno is not actually going to be looking at Io's volcanism at all. It doesn't have the instruments really to do that. However, the volcanic activity on Io is really relevant to the Juno mission because it can produce Io's atmosphere gets stripped off and ends up in the greater Jupiter environment in the form of neutral and ionized materials that may be relevant for the Juno spacecraft. And so certainly if we see a really large outburst type eruption, we will convey that immediately to the Juno team. But in terms of connecting science, one of Juno's main missions is characterizing these polar aurorae, which have a lot to do with the plasma environment around Jupiter. And one way that we can connect that to Io's volcanism is looking at kind of how the variability in the ion environment correlates with variability in Io's volcanic activity, and if that correlation exists or not.
And Vishnu, the Psyche is a metal asteroid, and that just kind of boggles my mind. I'm wondering if you'd talk a little bit about what the regolith on a metal asteroid is expected to look like. How is it different from the kinds of asteroids we visited before, and how would this impacting material interact with the stuff that Psyche is made of?
Sure. So, so the thing is that the density of Psyche is about 4.5 grams. It's metal, but which has significant porosity. I think the porosity is somewhere between 40 and 60% on Psyche itself. So we're not sure if it's an intact core of a protoplanet that got disrupted at some point in the past. The silicates that we see are very reduced. In other words, they were formed under conditions that we typically don't expect when you differentiate a parent body, something similar to the Earth or the Moon. So the kind of silicates we find are, it's not olivine that we would find because that is the layer you would expect on top of a core. Typically when you have a mantle core boundary, you see olivine and then you see the metal called nickel-ion metal core. In this case, we see pyroxene. So starting material for Psyche itself, I think, was not chondritic in traditional sense that we see for the terrestrial planets. So and then the question comes down to what happens when you have 4.5 billion years of impacts onto a surface that is rich in this. It is, we face this problem even when we try to grind up iron meteorites when we're trying to do regolith experiments in the lab for spectroscopy. My impression is that most of the objects in the asteroid belt have material that don't belong to those asteroids. And I think, the paper that came out a couple of days ago in Nature about the LROC results, where the whole lunar surface is churned up every 81,000 years, it shouldn't be that much different. I mean, things are slightly slow, not as energetic and active in the asteroid belt, but we see this in the meteorites as well. So we have a lot of contaminants on the surface. So I believe that's what we would see on the surface of Psyche. It would be just regular regolith combined with impactor material. And I don't think we can distinctly see iron metal regolith as distinct, locations on the surface.
Any more questions in the back, Rick?
Yes, this one is from Irene Klotz of Discovery Communications for Linda. What is the overall condition of the Cassini spacecraft right now? Are all the instruments still working?
Right now, the Cassini spacecraft is very healthy. The instruments are working. We did have to turn off one instrument, the Cassini plasma spectrometer, and this was some time ago. It had a short in it. But overall, the rest of the instruments and the spacecraft itself are working quite well. What's limiting the mission is that we're running out of fuel. And so that's when we end it, we'll be very, very low on fuel.
And then Kelly Beatty from Sky and Telescope also has a question for you, Linda. He asks, what's the total duration of the Cassini program from inception to its impending conclusion?
Total duration, that's an interesting question. I'll give two numbers. The instruments were selected, the announcement of opportunity went out, the instruments were selected in 1990. And if you want to know when did that first idea for the Cassini mission get started, you'd go back to the two Voyager flybys in 1980 and 1981. And it was really that flyby of Titan, we couldn't see beneath that haze, that really got the conversation going, both between the United States and Europe. It was Toby Owen, Wing Ip, and Daniel Gaudier who got together and got the community discussing the possibility of going back to the Saturn system with a probe for the Titan atmosphere. So you could go back all the way to the early 1980s.
And then Kelly Beatty from Sky and Telescope has a follow-up for Katherine relating to his earlier question about resolution. He says, so the spatial resolution sounds like it's comparable to the diameter of Loki's lava lake. So how can you determine that the locations of the hot spots are moving around one way or the other? Since you're seeing, basically you're barely resolving the lake.
Right. Certainly the lake is barely resolved. You saw the error bars on the plot that I showed, so those represent the uncertainty of where the peak of the emission is coming from. So we can get the locations by basically taking the centroid of the point spread function of the telescope and figure out where exactly the emission is coming from. And yeah, I mean, it's a valid point that it's barely resolved, but it's resolved enough that we can see just a vague motion from the top to the bottom of the Patera. And as represented by the uncertainties, it's only, a couple of sigma motion, but it is consistent between all of these different points. Every single point that was plotted, despite the large error bars, followed the same trend. And so that makes it a lot more compelling, despite this valid point.
I have a few questions myself, if I may. Rick Feinberg, AAS press officer. I'll start with Vishnu. You mentioned in your presentation that there are 800,000 asteroids in the asteroid belt, the main belt. Is that an estimate of how many there are, or is that the number that are known to date?
Yeah, those are the discovered asteroids that are known today.
And that number has gone up dramatically in recent years thanks to sky surveys, right?
Right, yeah.
Yeah. And then when you talk about water on asteroids, whether we're talking about, Ceres and Vesta or other asteroids, I think when you say we're finding water on asteroids, the public immediately thinks of puddles and ponds and things. But you're talking about molecules bound up in minerals. You're talking about water that's, potentially went straight from the gas phase, perhaps. Can you just clarify a little bit
Sure.
about what planetary scientists are really saying when they're talking about
Sure.
finding water on these rocky bodies.
Right. So it's definitely not liquid water, like you said. It's fascinating because when we got to Vesta on Dawn, I was on the Dawn mission as well, we had made a prediction based on what we looked at meteorites that Vesta would have significant amount of carbonaceous impactors. An interesting part about the reason why we did was when we looked at the meteorites from Vesta, the HED meteorites, they have a lot of dark inclusions that are carbonaceous, similar to CM chondrite meteorites. And we have some meteorites that are from Vesta that have more carbonaceous material than material from Vesta itself. And so when we try and study these meteorites in the lab, when you try and heat them, they lose a lot of volume because a significant portion of them material is water in their structure, not adsorbed water from the atmosphere, but structural water that is in the minerals itself that is primordial for the meteorites. And so from the Dawn results, I think there is about 5% water on the surface of Vesta, approximately, based on the absorption band and also the grand instrument that was around Vesta. In the case of Psyche, the absorption band is actually deeper than Vesta. So if you go to this 85-kilometer crater on Psyche and you scoop up some material and you heat it, you would obviously take the water out of it, and the volume of the meteorite actually shrinks, or the material would shrink. So you can't, in a sense, extract water out of these minerals, but you'd have to heat a lot of it for you to, have a drink.
Now, I have a quick question for Katherine as well. Are all the volcanic hotspots that you're seeing already known, or are you discovering new eruptions from spots on the surface that hadn't erupted before? Is that even possible to determine?
Yes, it is possible to determine. Almost all of the ones we've detected have been seen before, specifically by Galileo. But we have seen a couple completely new hotspots. And the ones that are completely new usually are ones that have these large eruptions. There's been some exceptions, but usually the new ones have large activity. So it's really interesting. There's been a couple cases where we can pretty well confirm that the eruption is taking place somewhere where activity hasn't been seen before.
So it's like a new fissure opened or a new volcano
Yes, right. And it would
something.
be really interesting to look at it again with spacecraft and see if we see a brand new surface feature in that location.
Another question for Katherine. Telescopes, of course, allocate their time competitively. You've spent a couple of years now looking at Io and documenting its variable behavior. Are you going to be allowed to keep doing that, or are they going to say, oh, now you've documented variability, you're done?
I hope so. So even though telescopes are very competitive, these observations at Gemini North, for example, they only take 20 minutes per observation. And so in one night of telescope time, say 10 hours, I can get 30 observations on different nights. And in addition, Io is so bright that we can make use of time, for example, during twilight, that a lot of extragalactic astronomers, for example, can't use. And so it's actually a great thing for the telescope to be able to use this time for science instead of having it sit idle. So I certainly hope that I will be allowed to continue making these observations.
All right, if there's no more questions from the floor, is there one from the back, one more?
Oh, yeah,
Before
Kelly
we
Beatty's
close?
got a lot of questions.
All right, let's do another 3 or 4. And then we'll
Okay,
close up.
so here's a follow-up from my question to Vishnu about water. He asks if the water retention has anything to do with the thermal inertia difference between regolith versus intact, more solid portions of the surface, or is it more a question of grain size versus surface area?
I think it depends if it's solar wind impactation. So thermal conductivity definitely is a factor when you have solar wind interacting with the regolith, especially when you're talking about OH bonding and forming H2O. But in terms of the retention of water from impactor material, it depends upon the velocity of the impactor. One of the common misconceptions we have is that all impacts have to be very high velocity, and that's definitely not the case we saw in Vesta, especially because we have all this material that is still hydrated and makes it to the ground, and it still remains hydrated even after the impact. If it's a high energy impact, then you expect the material to devolatilize. So that is a bigger factor, I think, than thermal inertia at that point.
Okay, I have a question, a couple quick questions for Linda. Are we going to get images from Cassini from this very interesting new perspective, coming down through the space between the rings and the planet? Or will the spacecraft be moving so fast that you really won't be able to get pictures because you can't focus?
We'll be able to get pictures, maybe not looking directly along the velocity line, but looking slightly off of it. Really great pictures of the rings of the planet itself, but there will be a problem with some smear because you're right, we're going very, very quickly as we go through these.
And then one of your slides, you mentioned getting a better estimate of the age of the rings. Based on everything that we've seen from Cassini so far, what's the current thinking? That the rings are quite ancient, almost primordial, or that they're a more recent phenomenon?
There are really two camps when it comes to the age of the rings. There's one group that look at the data, and there is compelling evidence, the brightness of the rings, some of the estimates of the surface mass density leading to an estimate of mass, et cetera, that point to young rings, 100 million years or so. And yet at the same time, there are other ideas that perhaps you could basically recycle material and perhaps you're breaking apart fluffy particles, providing a bright surface. There are some questions about the surface mass density in the most opaque, dense B ring. So the question is a little bit up for grabs. And in fact, I think we'll have some kind of we'll probably have people write down their best guesses and see who comes closest for guessing the mass of the rings.
All right. I believe that's everything, unless it's the last question from the floor. No, so I'd like to thank the panelists for coming and giving an excellent briefing, and for all of you for turning up. Have a great day. Thank you.